Dear students, welcome to Sia's digital classes. Today let us learn the concept of test of single proportions. So whenever we have single proportions in the data, how the formula will be, how the test procedure will be, let us have a glance today. So here is a formula first. Normal test can be applied to the fundamental property of normal distribution. Yes, we always take normal distribution always for a large sample test. From that we will drag for proportions. So formula for normal distribution, we know z is equal to x minus e of x by root over variance of x. That will convert into our proportions. Now how it goes on, let us check it out. So x minus np by root over np cube becomes our proportion, single proportion formula, because e of x for normal distribution we are considering here. So in binomial we'll get np, right? So np here, and in variance we have npq, so that we have substituted here. So we got the formula for a proportion, single proportion. So this becomes a formula for proportions, and we have taken formula from normal distribution, so standard normal. So we'll write comes from normal distribution with 0 comma 1. So that is your test for single proportion formula. Now let us check the conditions, how we got that proportions and all. So if x refers to the number of persons containing the specified attribute in a sample of size n, then the observed proportions of success is given by p is equal to x by n, or x by n is equal to p. That means here success and failures will be getting in proportions. So we are going for obtaining proportions in terms of x by n, where x n are the references, like persons, how many persons are containing out of the samples. So x by n becomes a probability p. So we are considering a binomial. Here I said e of x is binomial distribution mean np. So because here proportions are in the way of binomial population, so we considered binomial distribution mean and variances, and we are proceeding with this. So p is equal to x by n we are considering, so that we'll get our expectations. Now how mean we got, that also let us check it out. So hence expectation of p will be expectation of x by n. P is x by n. Just now we considered x by n as p, so I have substituted here. Now take 1 by n outside the expectation, so it went out, 1 by n remains 1 by n itself outside. So e of x as it is. Now e of x is the binomial mean. Just now we discussed success and failures we will be considering. So binomial distribution, x follows binomial distribution for us. So it's npx. I am considering binomial distribution with n comma p parameters. So our mean and variances we are considering. So e of x becomes our np. So I am substituting e of x np here. N will get cancelled. You will remain with the expectation of small p is equal to capital P. So you have to write properly here. Small p refers for the sample proportions, capital P for population proportions. So expectation of p, small p, I've got as capital P, that is proportions for population. So expectation of p we have done. Similarly, let us check it out, variance also or standard error. So let us check it out first for variance, then we convert into standard deviations or standard errors also. So thus an unreliable estimate regarding the population proportion capital P. See, I've just now I said capital P is population proportion. So population proportion is provided by the sample proportion P, small p. So also let us check how the variance of small p goes on. So variance of small p, that is p, we know x by n we have. So I have substituted variance of x by n. Now when I want to keep out, so n is a constant. When it goes out, it becomes its square. So 1 by n square I have kept out. Remaining variance of x as it is I have wrote. Now again variance of x, because it comes from the binomial distribution, variance of x is npq. So I am substituting npq here. Instead of e of x is substituting npq. So 1 n and 1 n will get cancelled. Leftover terms are variance of p is capital P into capital Q by small n. So that variance of small p I have got. Now I don't want variance of our formula for normal distribution. We need standard error over there. So let us convert variance into the standard error. So standard error of p is nothing but root over variance, we know. So simply take its answer and do root over. So root over PQ by n becomes our standard error. So standard error I've got and variance mean we got, a of p we got. Let us all substitute and let us get the z formula for single proportions. So in that way we'll obtain the z value. Let us check it out how we have obtained. Suppose x and its consequent x by n is a normal for large samples of size n, then the normal test employed for the proportion of success is given by. So formula, first of all let us write the formula, then let us substitute whatever the values just now we have obtained. So this becomes the formula of normal distribution. P minus expectation of P by standard error of P, small p, all the sample proportions. Now I have got expectation of P already I have done, and standard error of P also I have done. So take that value and substitute here. So that becomes our formula, what we discussed earlier, the same formula we got here. So z is equal to small p minus capital P by root over pq by n, which came again from the normal distribution with 0, 1 parameters. So here the same thing, how differently like limits and all, how we'll consider under single proportion, that also let us discuss. So in the second point let us discuss how the formula will change if the samples are drawn from a finite population. So let us check it out. If the sample is drawn from a finite population of size capital N, then the observed proportions of P is, so if at all I am considering a finite population with the size capital N, our formula will change like this. So standard error I am writing first here. Standard error of P will change as capital N minus small root over capital N minus small n into PQ, downside small capital N minus 1 by n as it is here. So PQ by root over PQ by n, the standard error as it is will come here because the sample size is finite. So formula will change here. The population size minus the sample size by population size minus 1 we have to consider whenever it is a finite population. So standard error will change in this way. So this becomes our second point. Whenever we have finite populations, we'll go for this formula. Now let us go for the third point. Here let us derive the limits, how the limits will obtain for the single proportion. So again it comes from the normal variate, that only we wrote. If normal variate x has a probable limits, so limits we are considering here. Limits, how it will goes on. So we know that mean and variances, root over variances will consider. So e of x minus 3 into root over variance, first limit. So negative value, then the positive value, next limit. E of x plus 3 into root over v of x becomes a limits for us. Then the observed proportion of success has the corresponding probability limits, if that is a values we are considering. So limits will be like this, it will go on. E of x mean value, that is E of p here in our proportions, and v of x root over v of x is nothing but standard error, and for proportions we are considering, so minus 3 into standard error of p it will be. The same thing here with the plus symbol. So this becomes a limits for us, and let us substitute the values of E of p and standard error also. So what happens, just now we discussed the standard error as well as E of x, that is mean value. So let us substitute that values and we get the limits for our single proportion. So what are that? So that is p minus 3 root pq by n, first value, and then the upper limit p plus 3 root pq by n. So this becomes a limits for the single proportions. So whenever we have mean and standard errors, so I have substituted and I've got value. Then what are they? Let us explain here. When p is unknown, the sample proportion p small p is considered as an estimate of capital P so as to determine the probable limits of the proportion. Thus, the limits are as follows. So, whenever P is unknown, capital P is unknown, the values will be these whatever the limits we got, that values will be considering same formula but for the sample proportions, because the capital P is unknown, right? So that values we don't have, but instead we have sample proportions. So what we do is the same limits, the same formula will consider for sample proportions. So simply capital P wherever we got, that is population proportions wherever we have, we can replace it with sample proportions, that is your small p minus 3 root over small p into small q by n. So simply replace population proportions with sample proportions. The same formula will replace the population proportions with the sample proportions. So that in that way we can get the limits whenever we have sample proportions with us. So that is the third point. So next, the same limits if you want to consider here according to the level of significance, because we discuss always here level of significance and critical values to accept the data or to reject the null hypothesis. So we need to take the limits according to the LOS. So let us check it out how the formula will change whenever we have LOS. So, but the level of significance, that is LOS, will call alpha. The limits of constant probability P are, so whatever the limits we are specifying according to the level of significance, if you want to change, so the same formula will change like this, whatever just now we discussed. Instead of minus 3, you have to consider Z alpha, because we are considering alpha here, level of significance we are considering. So instead of 3, we have to consider our Z alpha. And again Z alpha, how you will get? Based on the data, based on the question, will get it Z alpha. So through that we'll write the values. If at all that alpha percentage they specify for 5% or 1%, how it will be, how we are getting the limits, let us check that also in the next step. So here Z alpha refers to the significant or critical value of Z at the level of significance alpha. So let us check it out what are the values and how our confidence limits will get through this alpha percentage. So particularly for the population proportion capital P, if 95% confidence limits we want, it will change like this. 95% confidence limits, nothing but alpha percentage will be 5%. 95% confidence means leftover 5% becomes our LOS. So that is alpha is 5%. So for 5%, what is the table value or the critical value we have remembered? So for 5% LOS for a two-tailed test, we have a critical value as 1.96. So let us substitute that Z alpha here and let us get the confidence limits. So whenever they'll ask confidence limits, they'll ask for 95%, 99% like that, means alpha will be the leftover percentage, that is 95% confidence limits means 5% alpha will be. So critical value 5% we need to consider in our limits. So P minus Z alpha, whatever the Z alpha we have, that becomes a 1.96, because critical value, that is alpha is 5%, that is its critical value is 1.96. So I have substituted here. Leftover formula remains the same, that is root over PQ by N, and the second value upper limit P plus 1.96 root over PQ by N will be the 95% confidence limits. So whenever in the question, if they ask confidence limits, this formula we have to utilize if it is for 95%. Now similarly, let us check it out if it is for 99%, how the formula will change. So 99% confidence in limits means leftover 1% will be our alpha, right? So alpha will be 1%. That 1% its critical value, what it will be? So from the table value, that is critical value is 2.58 we know. So I have substituted that Z alpha as 2.58 and I have converted my formula. Check it out. P minus 2.58 root over PQ by N, and another limit P plus 2.58 root over PQ by N. So this becomes a 99% confidence limits. So this is the concept of entire single proportion, how the formula will obtain using our normal distribution, standard normal, and converting the formula and getting single proportion formula. Then its limits whenever Z alpha we have, that is critical values we have, and then through that the confidence limits for 95% as well as 99%, that all we discussed here. So this is a long type question, or is if they can ask for short type also. So have a glance properly and learn the formulas properly for your exam. So this is the concept of single proportion. So hope you have understood this session. See you all in the next video. Thank you.